Okay, Assalamu alaikum. Class. So the topic that we will be doing today is complex numbers. The first thing that we need to understand, how do we get complex numbers and when do we get complex numbers? Whenever we have a negative sign in a square root, that is what we call an imaginary or complex or not a real number. And how do we try to solve, simplify, and manipulate and understand complex numbers? We make the very basic complex number, which is under root of -1, and we call it iota. So, yeah. So under root of -1 is what we'll be calling iota, and then we'll be dealing everything in these terms. So for example, if you were to find what is under root of -4, you can break it in under root of 4 multiplied by under root of -1. So under root of 4 is plus minus 2. So you can say that we'll either get 2 iota or we'll get -2 iota. Is this clear? So now if I give you 2 plus under root of -9, again, right now I'm just giving you plus, but just for understanding the entire thing, I can say this will be 2 plus, because the question says plus. So let's just consider this plus for the time being. 2 plus 3 iota. How do I get 3? The root of 9 is 3, and there is already a addition sign over here. So under root of -1 is iota. So this entire thing can be written as 2 plus 3 iota. Now remember, because a number has a part of complex in it, the entire number is called a complex number. But that complex number can be divided into two parts. One of it is a real part and the other is an imaginary part. If I'm saying 2 plus 3 iota, yes, the entire number is a complex number. But what about 2? 2 is actually a real number, right? This under root of -9 is what is a complex number, right? Or an imaginary number. That makes the entire number a complex number. So we can split the complex number into two parts, and these are the notations that we will use to write the complex number. And we will say that the real part of z is 2 and the imaginary part of z is 3. Is this clear? Now we know that these are two separate parts, just like x and y coordinates are two separate parts. Similarly, the real and the imaginary parts will always be separate. They will never be together. So in order to understand that, we make an Argand diagram. What is an Argand diagram? It is the diagram that is used to simplify, manipulate, and analyze complex numbers. It basically keeps the real and the imaginary parts separate. And by keeping them separate, it helps you analyze the entire thing. Now, the x-axis is what we call the real numbers or the real axis, and the vertical axis or the y-axis is called the imaginary axis. So now once you have this number with you, which is the complex number, you have 2 plus 3 iota. You can simply plot it on an Argand diagram. And you will say, okay, so the number is, if I want to plot it in the Cartesian way, this is 2 plus 3 iota. So this is a complex number z. That is how you plot it on an Argand diagram. It's two scales on the 2 steps on the real axis and 3 steps on the y-axis. Now, one thing that you need to be careful about, especially regarding your A-level syllabus, because you'll be dealing with the complex loci later on. Whenever you try to sketch or make an Argand diagram, try to keep the x and the y-axis same. Their scale must be same. The ratio of their scales must be same, because that will help you understanding many loci. Is this clear? So this is a complex number z. Now you can do many things with it, and you will eventually have to do many things with it. First thing is the modulus of z. Now, what is the modulus of z? If I say modulus of z, it is basically the length between z and the origin. It is the length between the complex number and origin. That is called the modulus of z. Is this clear? How will you find it? Simply using the Pythagoras theorem. Take the real component, square it, take the imaginary component, and you square it. Make sure when you're taking the imaginary component, do not consider iota with it. Be very clear about it. Do not consider the iota with it. So if I want you to find the modulus of z, you simply take 2 square and then plus 3 square. This will give you the modulus of z. which is the length of z from origin. Is this clear? Is this clear, class? Now, the next thing is the argument of z. What is the argument of z? What is bearing? Bearing is an angle, right? An angle from the north to a certain line. Similarly, argument is also an angle. It is the angle that the complex number, the line between the complex number and the origin, makes with the positive x-axis. Okay, I'll show you one thing. It's a very good thing when we use autograph. When I click on modulus, I want to find the modulus of, sorry, my bad, argument of z. It asks me for a certain setting, reflex angle. If I'm not allowing the reflex angle, it will show me the modulus, which is 0.9828. It is the angle which we find in radians. Again, we can simply use basic trigonometry to find it. Tan theta is opposite, is the imaginary part, and adjacent is the real part in this scenario. The previous syllabus, the previous A-level syllabus followed this convention that the argument had to be an angle between negative pi and pi. That means that the argument cannot be an angle greater than 180 degrees or pi radians. So the moment you went in the third quadrant, for example, let me take an example. If I take a number which is -3 and -1. Now this is a complex number z2. If I want to find the argument of z2, and if I do not select the reflex angle, which angle will it show? It will show me the angle that the positive x-axis makes, and this will be a negative argument. Is this right? But now the syllabus has been updated. This limit is no more followed even in A levels. It says you can go for the angle beyond pi, and you can come in the anti-clockwise direction. Positive x-axis. Positive x-axis to the modulus line. Is this clear? Sorry, come again. From positive x-axis, anti-clockwise is positive and clockwise is negative. So the previous syllabus convention used to follow this, that the argument has to be between negative pi and pi. That means if it were in the third and the fourth, and even now for many questions, it obeys this convention that the argument has to be between negative pi and pi. So if it is in the third or the fourth quadrant, you always go clockwise. So, you know, so to make things easier and simpler for ourselves, there is nothing wrong in following this convention, but answers are accepted for reflex angles as well. Yes, from the positive x-axis. Is this clear, class? Next is the complex conjugate. If this is z, and I ask for a complex conjugate. What is a complex conjugate, class? See, when I click on the complex conjugate, which point did it show? What is the link between the original complex number and its complex conjugate? It is the reflection in the x-axis or the real axis. Just the sign of the imaginary part is what changes. And what is the notation? How do you write it? You put a small star on top and you call it a complex conjugate. Is this clear? So what is a complex conjugate? Reflection on the x-axis. In short, we can say that the sign of the imaginary part changes and we get a complex conjugate. Why do we need it? Again, we are not focused on this. We are interested in something else. Okay, class. Just taking an example. This is not a very bright example. This will just help you understand it. How do you add two complex numbers? If I tell you to add two complex numbers, z1 and z2, what will you do? The real part adds with the real part and the imaginary part adds with the imaginary part. For this one, I've taken the example of a complex number and its conjugate, but that is valid for any two complex numbers. Similarly, if you were to subtract two complex numbers, the real part and the imaginary part, they are like terms and they subtract likewise. What if you were to multiply the two complex numbers? Well, this is what I wanted to tell you specifically about multiplying a complex number with its complex conjugate. Multiply a complex number with its complex conjugate, what do you get? Yes, tell me, what do you get? When you multiply a complex number with its conjugate, what do you get? Remember, the square of iota is -1 because iota is under root of -1. So the square of iota is -1. Yes, so iota square is -1. 4 plus 9, which is 30. Now, this is a very important thing regarding complex number, that whenever you take a complex number and you multiply it by its complex conjugate, it's always a real answer. You'll always end up getting a real answer because iota will be squared, which will make it a real number. So a complex number multiplied by its conjugate will always give you a real number. And how do we use it? Okay, now another example. Again, in this one, I've taken a complex number and I've divided it by its own conjugate. Again, but don't worry about that. Just have a look at this example. What is happening? The two complex numbers are dividing. Now, if I ask you, can you tell me the real and the imaginary part of this entire result? You cannot. Why? Because there is a complex part in the numerator and the denominator, a real part in the numerator and the denominator. So you cannot just differentiate between the complex and the real part. But what if you were to complete the denominator into a real part? And how can you do that? If you multiply the denominator by its complex conjugate, you know that the denominator will become real. But you just can't take a fraction and multiply the denominator by anything. If you multiply the denominator by anything, you also have to multiply the numerator with the same thing. Again, your target is to convert the complex in the denominator into a real number. And how do you do that? You multiply it by its complex conjugate, and the same operation you have to do it with the numerator. Eventually, you end up getting this number. Now you can just separate out the real and the complex part. So the real part is -5/30 and the imaginary part is 12/30. It becomes a real number. And it is used in converting these kinds of complex number divisions. Whenever you were to divide two complex numbers, you always have to multiply the denominator with its complex conjugate, and the same operation has to be carried out with the numerator. Is this clear, class? Okay, now I want you to use the quadratic formula and solve this equation. Okay. Use the quadratic formula and solve this equation. Remember, does this equation have any imaginary part? Do you see any imaginary part in this equation? Yes, class? Is there any imaginary part in this equation? No, the equation consists of all real parts for the time being. But if I tell you to solve this equation using quadratic formula, you're using a calculator, you can convert your calculator into complex mode and then solve this equation, because the calculator will not give you any answer if you're not using the complex mode. That's it. Quadratic formula, -b plus minus under root b square minus 4ac upon 2. Go to equation second or the third equation. It will be written ax square plus bx plus. What two answers do you get, class? Yes, 7 plus 2y and 7 plus 2 iota. Yes, 7 plus 2 iota and 7 minus 2 iota. So that is a very important thing here. Whenever you are solving an equation, remember now the equation, if the equation does not have an imaginary part in it, if you get one complex root, you'll definitely get another complex root which will be its complex conjugate. And when is this concept or logic valid? Whenever you have an equation which does not have an imaginary part in it. Is this clear, class? The complex roots for these equations are found in pairs. If you know one complex root, the other complex root will just be its complex conjugate. Is this clear? Take any equation and if you solve it, if you're getting one complex root, the other will always be its complex conjugate if the equation does not have a complex or an imaginary part in it. Okay, class. Now let's go to polar coordinates. This is just another way of writing down the complex number. If I give you a complex number 3 plus 4 iota, you can simply tell me that its modulus will be, I'll take new complex number page. I'll say let's write the complex number 3 plus 4 iota. Okay, you already know that this is a complex number, but polar coordinates, again, there is a kind of x's which involve polar coordinates. If I tell you it's a polar grid, and that's an entirely different grid, you don't have to deal with the grid right now. But that you need to understand another way of writing down the complex number. So what do you do again? If you consider the adjacent side, which is 3, and the opposite side, which is 4. So your hypotenuse is what we are calling R. The hypotenuse is what we are calling R. So the adjacent side can be written as R cos theta, and the opposite side can be written as R sin theta. Again, having a look at this example. This is the polar coordinate form, and if I expand it, it's R cos theta plus iota R sin theta. So the real part is R cos theta, which is 3 in this case, and the imaginary part is R sin theta, which is 4. Again, R is, I just told you in the figure as well, or the constant. R is the modulus. R is the modulus on, if you look at the Argand diagram, so you can just simply square 3 and 4 and get the value of R, just like we got in the harmonics for trigonometry. The same concept we'll be using here. The value of R, and similarly, theta is the argument, which you can find when you know the complex number, and if you just imagine the Argand diagram, you can find theta and R very easily. The same polar coordinates can also be written in this form, which is RE, which is the Euler number to the power iota theta. So if it's given to you in this particular form, you can always write it in this form or convert it into this particular form, which is called the Cartesian form. 3 plus 4 iota is called the Cartesian form. Iota is already there. See, now the same number, if you were to write it into in polar coordinates, this 3 is the real part and this 4 is the imaginary part. Yes, obviously. See, 3 is the imaginary part and 3 is the real part and 4 is the imaginary part. Right? R is the modulus and theta is the argument. Instead of writing 3 plus 4 iota, you can write the entire complex number using its modulus or the magnitude and the angle or the argument that it makes. Is this clear? Clear? Just giving an example again. Once you figure out the entire thing on an Argand diagram, you can easily understand that R is the hypotenuse and you're using it, the adjacent and the opposite and the perpendicular at the base to find the value of R and the value of theta. Okay? So try to link it with, okay, 2 more things. Now these are 2 complex numbers. Again, see, how do you find the argument? Highest. Yes, argument is theta. Polar coordinates are just another way of writing down the complex number. Now for the same complex number, what is your R? R is 5. So the same complex number 3 plus 4 iota, this is called the Cartesian form. You can write it as 5e to the power iota. And what is your theta? Tan inverse of 4 over 3, you'll get an angle in radians. You can write the entire complex number in this short form, which is the polar form. Is this clear? Opposite upon adjacent. 4, adjacent is 3. Again, if I tell you things become very easy for you, then you start linking them to the Argand diagram. Okay, class, I've given you two complex numbers here, Z1 and Z2. I want you to do one thing. I want you to find me the product of Z1 and Z2. Can you find the product of Z1 and Z2? The product of the complex numbers. You can find the product of these. Let's just go with this, cover this theoretically. Okay, now the relationship that you want to study here is this, which is very frequently used. If you find the magnitude of the product, Z1, Z2 is the product of the complex numbers, right? The magnitude of the product will always be equal to the product of the magnitudes. I repeat, the magnitude of the product will always be equal to the product of the magnitudes. If you were to find their magnitudes individually and multiply them, you'll get the same answer that you'll get by finding the product of the complex numbers and finding its magnitude. Similarly, the quotient or the ratio of the, if you're dividing two complex numbers and then finding its magnitude, it's the same as dividing their individual magnitudes. Is this clear? This is just an example that I've given you. You can verify it with this example later on. Anything that is not clear till this point, let me know. This is a very easy example to verify. The magnitude of Z1 is 5. The magnitude of Z2 is 10. So if you find their product, the magnitude of the product is 50. You'll be getting the product as 50 iota. Product kya aa rahi hai? 50 iota. So the magnitude of 50 iota is 50. Origin से distance देखो कितना आएगा? 50 आएगा ना, right? When you multiply what? Complex numbers? What do you get? Iota का square करो -24 हो जाएगा. 24 and 24, so you're left with 50 iota. Okay. Similarly, if the argument of the product is equal to the sum of the arguments, and again the argument of the quotient is equal to the difference of the arguments. Again, these are very frequently used relationships. Hence, we write them down because we'll be using them quite frequently. Is this clear, class? Again, this is just an example that I've given you. You can use this example to verify all these relationships, and you'll be understanding that yes, you're getting all of them as the same answer. Now let's go through this question. Sorry? Yes, argument of Z2 upon Z1 will be equal to argument of Z2 minus argument of Z1. Now let's have a look at a very easy example to understand this entire thing. It is given that the complex number -1 plus under root 3 iota is the root of this equation. Do you see any imaginary part in this equation? The question is telling you K is a real constant. So do you see any imaginary part in this equation? The first part is asking you write down another root of the equation. What will be that another root of this equation?
Conjugate.
What will be the other root of this equation?
The conjugate also.
The complex conjugate of the root that the question has already told us, that will be -1 minus under root 3 iota. Right? Now the question is saying they find the value of k and the third root of the equation. If the question has provided me with the root, we did this even in remainder factor theorem. If the question has provided me with the root, can I find the factor? Root means x is equal to this entire thing is a root. So what will be the factor? The factor will be x plus iota minus under root 3 iota. And the other factor will be x plus 1 plus under root 3 iota. And the third factor will be a cubic factor, which I am writing as ax plus b. Now, there are many ways to do this. You can either expand this entire thing, which you will eventually have to do, and then compare the coefficients, okay? You know these are the two factors, agreed? And the polynomial is cubic. The polynomial is cubic. The root is x is equal to -1 plus under root 3 iota, right? So what will be the factor? If I tell you x is equal to 2 is a root, so x minus 2 is the factor, right? If x is equal to 5 is the root, x minus 5 is the factor. Similarly, if the question has provided me with the root, can I say this entire thing is a factor? This is one factor, this is the second factor, and the polynomial is cubic. And these are two linear factors, right? If these are two linear factors, the third factor will also be linear, because three linear factors can make an entire cubic polynomial. Now, all you need to do is expand and compare the coefficients for 6 marks, and the entire question will be solved. Compare the coefficients. So expand the right side. It's very easy. It looks complicated and difficult, but trust me, it is very easy. I want you people to do it once on your own, and then I'll guide you. So let's see what was the smarter way to expand this entire thing. If you observe carefully, you see that it's a minus b and it is being multiplied by a plus b. So we can just directly write the entire thing as a square minus b square. If you observe carefully, it's a minus b and it is multiplied by a plus b. So you can directly write it as a square minus b square. If you want, you can individually expand it as well. So this is a quadratic factor that you get. Then you multiply it by ax plus b. This is what you get. Then you compare the coefficients. You get your values of a, b, and k. So what is the third root? The third factor is 2x plus 1 in this case. So the third root is -1 upon 2. Is this clear, class? Okay, let's go through another example. The question has provided us with u 8 minus 15 iota, and the question wants you to get the two exact square roots of u. Okay, now देख लो जरा next one. ये वाली चीज कभी नहीं समझ आती है. Okay, so I'll say that the square root of 8 minus 15i will be equal to a plus iota b. Now remember, all I need to do is figure out the value of a and b, right? I can square both sides. And then I can just compare the real and the imaginary part. My real part is a square minus b square, that will be equal to 8. My imaginary part is 2ab, that will be equal to -15. And then we can easily make one of them the subject of the formula and solve to get the values of a and b. You could have also converted the entire thing into a polar form and then found the under root. Even that is another way. That is obviously a more convenient way, but for the time being, for the learning process, let's just focus on this one right now. Is this clear, bachcho? The question said under root of. So once you get the values of b, you also find the corresponding values of a and b. Then you can find the two roots easily. Again. No, we'll get the value of a. And for that particular, remember a is negative 15 over 2b. So once I find a, I put the value of, once we find b, we put the value of b in this one and figure out the value of a. So if a is negative, b will always be positive in this case, because a is negative 15 upon 2b. Okay. Let's have a look at this question. Again, u and v satisfy the equation this. Solve the equations for u and v, giving both the answer in the form x plus iota y. You can make any one of them the subject of the formula. You can make u the subject of the formula from the first one and put it in the next equation. So this is what you get. Now there are two ways of approaching this one after this step. Again, there are many other ways as well, but using the Cartesian forms, there are two ways that we can devise from this step. Okay, we either take v common, or we write this entire thing as 5 over 1 minus 2 iota. And then we multiply it by the complex conjugate of the denominator. That is one way of doing it. Or the other way of doing it is that we already know that the final answer for v will be x plus iota y. We can plug it in this x plus iota. Sorry? Yes, two different methods. After this step, we already know that v is x plus iota y. We can plug it in v and then compare the real and the imaginary part to get x. And obviously that is a longer method. And this is an easier or a shorter method. Once you figure out v, you also need to find u. Clear, class?
Yes, sir.